Hello everyone. Today we're going to learn a little bit about electromagnetic radiation. A reminder about what emission and absorption spectra are and what they look like. Atoms and molecules interact with light, and when they do, will produce either an emission or an absorption spectra. Emission spectra are generated by excited electrons releasing their energy and going to a lower energy state. This produces lines of light with specific energies, as shown to the right on this slide. The one on the right is the emission spectra for hydrogen. Absorption spectra are produced when electrons absorb the light energy shown on them and in doing so move to a higher state. These have an opposite appearance to emission spectra. Instead of there being bright lines where the energy is being absorbed, there will instead be dark areas or dark lines where things are missing from the full light spectrum. This is because those specific energies have been absorbed. The reason that emission and absorption spectra are important is they have provided evidence for what electrons do. Niels Bohr observed that the hydrogen always produces the same emission spectra, the one that we have already seen on this PowerPoint, and other elements also produce their own unique spectra every single time. Therefore, he came to the conclusion that electrons must exist in orbitals that have discrete energies, and that electrons can move between these orbitals by either releasing or absorbing energy. When they release, they go to a lower energy orbital, and when they absorb, they go to a higher one. So, in order to learn more about emission and absorption spectra, we must first learn more about light itself. Light, the full electromagnetic radiation spectrum, is quite large. You'll notice we only see a very tiny fragment of it. We see only the visible light part of the spectrum, whose wavelengths are from around 750 to close to 400 nanometers, give or take a few nanometers on either side. These consist of all the visible colors of light that we see on a daily basis. All other pieces of the electromagnetic spectrum are invisible to human eye, but are picked up by some animals whose eyes have different structures in them. The higher energy light spectra would be ultraviolet, X-ray, and gamma rays being the most energetic, while the lower energy rays would be infrared, radar, or microwave, and also the radio waves of various kinds. Since light is a wave, it has all the properties of a wave. So we are going to quickly go over some of the main characteristics and properties of a wave. Waves have amplitude, which is a measure of the height or magnitude of the wave. It is measured as a distance from the top of the peak or crest to the bottom of a trough. The amplitude has an impact on various aspects of the wave. For example, a higher amplitude sound wave sounds louder to a person. Waves have a wavelength, which is a measure of the length of the wave, usually measured from one peak to an adjacent peak. This can also be measured from other equivalent points. It's just that measuring from peak to peak is usually considered easy and is therefore usually how the measurement is collected. Waves have a period, the length of time it takes for one wave front to pass by. So this would be starting your timer when the crest of one wave comes, and then stopping it after the crest of the next one comes. Waves also have frequency, which is the number of waves that pass by in a given unit of time. Traditionally, this unit of time is 1 second. Frequency is the reciprocal of period. Waves have a speed, which is a measure of how fast they are moving. Since we are going to be talking about light, we will be dealing exclusively with the speed of light, which is equal to 2.99 times 10 to the 8th meters per second. The two aspects of the wave we will focus on most closely will be wavelength and frequency. Wavelength and frequency have what we call an indirect or inverse relationship. As one of them gets bigger, the other shrinks. This makes sense. If a wave is very long, it is going to take quite a bit of time for it to pass by, and so not many will pass by in a given time interval. A long wavelength means a small frequency. Conversely, if the wave is very short, many wavelengths might be able to pass by in a given time interval, which means that a small wavelength would mean a high frequency. There is a mathematical formula that connects wavelength and frequency. This formula is c equals lambda times nu, where c stands in for the speed of light, again 2.99 times 10 to the 8th meters per second. This is a given constant for the speed of light in a vacuum. Lambda, a Greek letter that looks vaguely like an upside-down Y, stands in for the wavelength. Please note that the wavelength must be in meters in order to use this equation. And nu, another Greek letter that looks vaguely like a V, stands in for frequency. Frequency is measured in either inverse seconds or hertz. These two units are equivalent to each other. So let us look at an example of how to calculate using this equation. Calculate the frequency of a photon, or a packet, of light with a wavelength of 656 nanometers. Please note this is in nanometers and the equation requires us to be in meters. We will have to do a small conversion in order to use it. Our equation is c equals lambda nu, and we are being asked to find frequency, which is nu. The easier thing to do would be to solve this equation while we still have the variables, since the numbers here are going to get lengthy and have a lot of scientific notation involved. So if we divide both sides by lambda in order to isolate nu, we get that nu is equal to c divided by lambda. So now let us plug in what we know. Nu is equal to c, the speed of light, which is a given constant, 2.99 times 10 to the 8th meters per second, divided by the length, now transformed into meters. Remember that 1 nanometer is equal to 10 to the negative 9 meters, and since it has a decimal point at the end, I can move it around a little bit to make it 10 to the negative 7 here. So the length is 6.56 times 10 to the negative 7 meters. If I divide these two, I will receive the answer. The frequency for this kind of red light is 4.56 times 10 to the 14th hertz. You could have also used inverse seconds here. Please note, I rounded to 3 significant figures for this because the wavelength that I was provided also had 3 significant figures. Because the speed of light is a given constant, it is considered infinitely precise and thus is not generally considered when you're determining significant figures.